Hello. My first purpose in this video is to talk about the question in the title, why is a to the half equal to the square root of 2? But to do it properly, because I found that the school textbooks I've looked at make rather a poor job of it and miss out on the opportunity to talk about a key way in which mathematics works. So my second purpose is to talk about that key process in mathematics by using some other examples. And in doing so, I shall answer all these questions. And it turns out they all have the same answer. So the process I'm talking about is this. When we're doing mathematics, we make definitions and write down axioms and then prove some theorems. And on the basis of that, prove some more theorems, perhaps some more definitions and some more theorems. And we build a whole structure. But the point about that is that in doing that, we make choices about the definitions and axioms that we use. There's a nice quote from Leopold Kronecker, a 19th century German mathematician who wrote something that I've translated as God made the whole numbers, everything else is the work of humanity, which emphasizes the way in which the structure of mathematics that we've created depends on a whole range of human choices. So I'll start with a very simple example. One of the questions that bounces around the internet from time to time is a square a rectangle? Well, square and rectangle are English words, and words in the English language have meanings that are imprecise and volatile, and there's really no way to answer a question like that in ordinary English. That's not good enough for mathematics. So in mathematics, we define words with much greater precision. But this time, we actually have a choice, don't we? So when I say a choice of definitions here, I don't just mean that we have two possible ways of wording definitions for the same concept. We actually have two different concepts to define. So I think we all know what a square ought to be. So there are many ways to word a definition of the square. There's mine. It's a plane quadrilateral whose four internal angles are all right angles and whose four sides are all equal. But we have two different definitions of rectangle available. So what I've called the inclusive definition here, a rectangle is a plane quadrilateral whose four internal angles are all right angles. So if we adopt that definition, then a square is going to be a special case of a rectangle. And the exclusive definition, well, it's exactly the same, except that it ends but which is not a square. And so if we adopt that definition, squares and rectangles are completely different. So how are we to choose between these two definitions? Well, the answer is we try them both out and see which one we like best. And we like them best on the basis of the theorems that we prove and the mathematical structure we create. So here, for example, is a nice theorem if we adopt the inclusive definition. We take any old rectangle and cut it with a line parallel to two of its sides. What we end up with is two rectangles. Well, that's a very simple theorem encapsulating a really quite simple truth, and it's very easy to prove. What happens if we adopt the exclusive definition? Well, when we divide a rectangle, we either get two rectangles, or a square and a rectangle, or two squares. And furthermore, when we divide a square, we get two rectangles. So that's a much more complicated statement, and what was originally seemed like quite a simple truth has become something rather complicated and messy. Well, that looks like a win for the inclusive definition. And it's for that sort of reason, in fact, that we always adopt inclusive definitions like that in our mathematics. So a square is a rectangle, is a parallelogram, and so on. But not everybody has to make the same choices. And on another planet, the local intelligent life form might adopt a different definition. And then mathematics would be just as valid. Okay, so that's not a very important example. The next one is much more important. So we asked before, what do we want the word rectangle to mean? Now we're going to ask what we want these symbols to mean. Okay, well, let's see how we get to that question first of all. So we start out with defining just a squared as a shorthand way of writing a times a. And then we advance to a cubed being the shorthand way of writing a times a times a. And then we can say, okay, well, we'll have a to the n as the product of n a's. And so now we have a definition for a to the n whenever a is a real number and n is an integer that's at least 2. We haven't done any real mathematics yet. All we've done is made a definition. But it does enable us to prove some theorems. And here they are. So these are the index rules. And these are true whenever a is real and whenever n and m are integers at least 2. And in this case, we need n minus m to be an integer at least 2, because otherwise that doesn't mean anything. Now, of course, these theorems are all extremely simple to prove. They all have simple one-line proofs. So let me just show you a couple of those. So this one here, a to the n, we've defined to mean n lots of a, multiply it by m lots of a, and that gives us n plus m lots of a, which accords with our definition of what a to the m plus n is. The next one is slightly subtler. Again, we have n lots of a, but this time divided by m lots of a. So long as n is bigger than m, this is n minus m lots of a. And so long as n minus m is at least 2, that accords with our definition of a to the n minus m. And the others are very similar. Now, in this video, I'm going to repeatedly come up with slides like this and not go through all the detail. I shall pause long enough that if you want to look at the detail, you can pause the video and go through it. But so here we have the proofs of the 4 index rules in the case when a is real and n minus m are integers, and n minus m is also greater than or equals 2 in this case. So where do we go from there? Well, the first thing we do is kick ourselves for not having defined a to the 1 to be a right from the beginning. That's an obvious definition for what a to the 1 should be, and the power rules still work, and exactly the same proof works. So that brings the rules down to 1. It's not quite so obvious that a to the 0 has to be 1, but again, if the power rules then work just the same way, and the proofs more or less work, so long as you understand that multiplying by no a's is the same thing as multiplying by 1. So we get it down to non-negative integers. Okay, so where do we go from there? Well, I'll tell you what we don't do, which is what the textbooks do. So this is a particularly clear example of how not to do it. So they assume that these results we've just proved for positive non-negative integers are true for all values of n and m. And then, well, then if you do make an assumption, you can work out what the others have got to be. So x to the minus m, you can work out quite simply that x to the minus 1's got to be 1 over x, and x to the minus m's got to be 1 over x to the m. And you can work out the fractional ones as well, and work out that x to the n over m's got to be the nth root of x to the m. But that's not how you do mathematics. That's terrible. So it's like saying, oh, I assume it's not going to rain this afternoon, so therefore I don't need to take an umbrella. Oh, that's a perfectly consistent worldview you've got there, just that it might be wrong. And the fact that you haven't yet proved it wrong doesn't mean that it's right. And just the same way here, if we assume all those rules work, we get a nice consistent worldview, but that doesn't mean it's right. So what do we do? Well, that line of argument isn't without its place, but we start first with wondering. We wonder whether we could define negative and fractional powers so that those rules would still work. Well, and if we do that, the line of argument that the textbook produces tells you that there's only one way you can define these things, so it could possibly work. And those are the rules, those are the definitions we'd have to adopt. So then we say, okay, well, let's try defining them that way, in a trial sort of way, and see whether that works. In other words, see whether it sets about proving all the rules. And if it does, then we shall definitely like those definitions and stick with them. It turns out we can do that. So let's look at these proofs. So I'm going to use some notation. I'm going to use P and Q as positive integers, little n and m as non-negative integers, and big N and m as integers of either sign. And our starting point is that we've got these 5 rules working for n and m non-negative integers, and so long as m is bigger than n, at least n in this one. Okay, so now we're going to start with the negative integers. We've worked out that we're going to have to define a to the minus m to be 1 minus a to the m. And so now we know that this little one here, where that odd exception, works for all negative n and m. And so now all 5 rules work for non-negative n and m. Does that make all the rules work for integers of either sign? Well, that's a big ask, and we don't know that until we work it out. So let's work it out. So one of the things we'll have to prove is that if we have negative integers, negative indices here, you can add them to get the product. Well, let's see. So a to the minus m, according to our new definition, is 1 divided by x to the a to the m, and that's 1 divided by a to the n. By the rules of ordinary arithmetic, that's 1 divided by a to the m plus a to the m times a to the n. Now, by the positive index rules that we've already proved, that one is a to the n plus m. And that accords with our new definition of a to the minus n plus n. And then we play that index a bit and we get a to the minus m plus minus n, which is what we wanted to show. So this illustrates how we can prove all these things. In proving these things, we can use the ordinary rules of arithmetic, and we can prove the index rules. We can use the index rules we've already proved. Now, I am going to whistle through these a bit. And again, you can pause and look at the detail if you wish. But we also need to prove, of course, the case when one of these indices is positive and the other negative. That works in just the same way. And then actually the division ones are quite cute, because we can do positive and negative together now, because whether n is positive or negative, a to the n is 1 over a to the minus n. And so we can use the multiplication rule that we've already proved to establish this one. Now, there are 4 cases of this rule, aren't there? Of which we only know the one where n and m are both positive. So we have to prove the other 3, and there they all are, using, as usual, the rules for positive indices. And these two are very similar and very similar to each other. Okay, so having done that, we've established that the index rules do work for integers of either sign. Okay, so let me get on to fractional indices. So we've worked out by playing with the rules in our wondering phase that that's going to have to be what a to the n minus p is going to be, a to the m over p is going to be. The question is, does that make all the rules work for rational indices of either sign? Well, let's find out. But actually, before we do that, hold your horses. There's something else we have to do. Is this a well-defined concept here? Well, first of all, it's only going to work for a positive, at least when p is even. But also, we've got a definition now for a to the m over 1. Well, but we've already got a definition for a to the m. They'd better be the same, or we're in trouble. Well, our new definition for a to the m over 1 is the first root of a to the m, and that is a to the m, so good, we're okay. In the same way, we've got a new definition for a to the, shall we say, 2/6, which had better be the same as the definition for a to the 1/3. Well, it is not absolutely trivial. So this thing is by definition the qpth root of a to the qm. So by the way surds work, we can assert that the qpth root is the pth root of the qth root. And meanwhile, by the index rules we already know, this can be written that way as a to the m to the power q, and then that unzips as a to the m over p. So there, it's okay. So now let's look at the proof for this. So a to the m over p times a to the n over q, by our new definition, that's the pth root of a to the m times the qth root of a to the n. Now, the way to make progress on this is to raise the whole caboodle to the pqth power. So the pqth power of that is the pqth power of that. Now we've got integer, in fact positive integer indices here, so we can use the rules we already know for dealing with them. So first of all, we can distribute this over that multiplication and get that. And then we can use the fact that this is the qth power of the pth power to get that. And then we can use the rule about a to the m to the q being a to the mq to get that. And then we can use the addition rule that gives you that. So that's good. And then we can go back to taking the pqth root of all this lot again, and we get this is equal to the pqth root of that, which accords with our new definition of that quantity. And then fiddling with the index, you get that. So yes, that's true. Good. The division rule is exactly the same. You just replace multiplication by division, and this plus becomes a minus. So that's easy. This one's quite complicated. Same idea though, raise it to the pth power. I won't go through the details. Pause it if you'd like to go through it yourself. And then this one, again, is very simple, using the way surds work to get that and the rules we already know for integer indices. And of course, that's very similar. And so we end up with this. The index rules do indeed work for rationals whenever a is positive and r and s are rational. So let's remind us how we got there. What we didn't do is assume these things are true and work out what the indices have got to mean. What we did is what mathematicians do, is that we made a definition, but we did do some playing around and wondering to work out what those definitions probably ought to be. But then we make the definitions and then we prove the rules. Now these rules are so powerful and beautiful, it's quite inconceivable that any intelligent species on another planet would come up with any other ones. So although we had a choice, really there was only one way to do it. My next example is one where this particular intelligent species has taken quite a long time to make up its mind. So is 1 a prime number? Well, history is quite interesting, actually. So for the ancient Greeks, the question is not asked because 1 isn't even a number. Well, what do we mean by that? What we mean is that the word that they use that we normally translate as number actually meant plural number. That is to say 2, 3, 4 and so on. 1 was the monad and not one of those things called numbers. And so the question of whether 1 was a prime number just never arose. They couldn't really ask it. Eventually, though, it was accorded the status of a number, and then its primeness was a question. It remained undecided for centuries. And of course, what I mean by that is not that nobody could prove it one way or the other, but that people couldn't make up their mind which way they wanted it to go. So some authors defined 1 as a prime number and some didn't. And to be honest, it doesn't matter much. You will hear it said that, if you allow 1 to be a prime, that fundamental theorem of arithmetic isn't true. So the fundamental theorem of arithmetic is the one that says that any positive integer can be uniquely expressed as the product of primes. Well, of course, that's not true if 1 is a prime, but it's easy enough to fix. You just say it's a product of primes bigger than 1. And to be honest, it really doesn't make much difference. But somewhere around the middle of the 20th century, mathematicians did finally decide that 1 should not be regarded as a prime. Famously, G.H. Hardy changed his mind on this between the 6th and 7th editions of his book, A Course of Pure Mathematics. The 7th was published in 1938. So before that, 1 was a prime, and afterwards it wasn't. And by the way, if you haven't looked at this book, you really should. It's a wonderful book. It was first written in 1908, and it transformed the teaching of mathematics at English universities. When I was an undergraduate in the late 1960s, it was still a recommended textbook for undergraduates, and it's still regarded as a very good book for covering the topics that it does cover. It's a lovely read, and of course now it's out of copyright, so you can easily download it and read it. And if you haven't read it, I thoroughly recommend that you do. Anyway, back to the topic. The matter about whether 1 was a prime or not was really not decided by reference to numbers, ordinary counting numbers at all, but by reference to more abstract algebraic structures. So the things one studies at universities, rings and integral domains and what have you, in that context, it's sensible to define things called units, which are elements which have a multiplicative inverse. So nowadays we divide the positive integers into units, of which there's only 1, namely 1, and the primes and composites. So in some sense, the Greeks were right all along. 1 just isn't one of those numbers about which the question of whether it's a prime or not arises. So it isn't a prime. But again, on another planet, the local intelligent species might make a different decision there, and it really wouldn't matter much. So my last example goes way further back in our mathematical education. So why is negative times negative equal to positive? And the answer is really because we've decided it gives the prettiest theorems. We like it that way. So let's just go through that. We start by defining addition and multiplication on positive integers. And then we discover some rules, which we nowadays call commutativity, associativity, and the distributive rules and so on. And then we go through wondering again. Wonder if we could create answers to these puzzles for all positive integers that would preserve these rules. And the answer is yes, we can, but only if we define negative times negative equal to 1. And when we do that, we open up the whole wonderful world of mathematics. And in fact, if an intelligent species on another planet made a different choice here, they'd never really get their mathematics off the ground, would they? They'd never get beyond counting. It's just hopeless. And so there we are. I said at the beginning that I would answer these 3 questions and that they all have the same answer. And of course the answer is because we like it that way. It's an aesthetic judgment largely. Certainly in this case here, and in the one I started with about the rectangles, it's just because I think it's a prettier answer really. And for the others, there's really no sensible alternative. And so although there is a choice, there's only one sensible choice.